more embarrassed than I would be anyway. This is too generous. I mean, I feel here in the company of some of my scientific heroes, and I'm asking myself why I'm even here. Well, later on, you gave part of the answer. There will be a slide when I will have occasion to clarify that a bit. But now let's just see what I plan to talk about. A warning, I should start like that. Don't expect new results, but also don't expect an unbiased overview over this field of finite model theory, many-value logics. I simply couldn't give you an unbiased overview. So in other words, it's not that kind of talk. I can sympathize much better with this guy. So I'm afraid I'm asking you to watch me scratch my head and speaking loudly while I'm doing so. So we will consider some better known challenges to the field, and hopefully I can also come up with some less well-known challenges. I want to emphasize differences to the classical case, to classical finite model theory. So I want to take the many-valued part here particularly seriously. And be warned again, it's quite selective and even speculative at certain points. Concretely, I have 6 sections, and there's only one slide for each of these sections of questions, of challenges. And hopefully that will allow me to give sufficient time for discussions. So a list of just problems, open problems, challenges could easily be a bit boring, I'm afraid. And therefore I thought I will start by provoking you, by provocation. I want to ask you seriously whether there isn't room for the finite model theory of propositional many-value logics. And I immediately admit that this sounds absurd, right? Because after all, the finite in finite model theory does refer to finite domains. And where the models here and where's the place for finite, it does sound a bit absurd, but be with me. So what is finite model theory about? Well, it's about many things, but I hope it's not controversial if I say that what we study is expressibility of logics with respect to finite structures, right? So what about allowing sets of assignments of values to variables? Well, actually propositional variables here. What if we consider this as a kind of structure? And differently, maybe somewhat more generally, what about this set of definable truth functions? Now, in the Boolean case, in the classical case, for example, this definable truth function, well, it's just all Boolean functions, right? And there's not much to play around with in terms of expressibility. And also the assignments, well, it's just binary assignments, so you can identify them with sets. Not very interesting. But in the many-valued case, if you are willing to consider this, the finite infinite distinction certainly makes sense now, because after all these possible values, it does make a lot of difference if you have a many-valued, a finitely valid or infinitely valid logic, right? And then asking which sets of assignments are actually expressible by given many-value logic is much less trivial than asking the same question for classical logic. Think about girl logic, for example. It's well known, this girl logic distinguishes orders of values rather than fixed values. So here you have a simple example, seemingly very simple, but it turns out that even with orders, it's not that simple, because if you want to make a distinction between the strict order and the non-strict order, you don't have enough expressive power in good logic. You need language extensions, and these are useful. This is not a question without relation to important questions. Other problems. it's useful, for example, to get interpolation, to consider certain type of language extensions that are increasing the expressibility in that sense that I'm alluding to here. So, for example, a paper by Butts and Fight already from '99 is clarifying that. Some of you, but probably not all of you, will know this book. This is the title of a book, actually the English translation of a book by Karpenko, Lukasiewicz's Logics and Prime Numbers. So this indeed is also about a kind of, well, let's say let's say expressibility of specifically addressed to finite valued Lukasiewicz logics. The title can easily be explained by the fact that there's an really old observation, so I think it's from 1970, if I remember correctly, that a Lukasiewicz logic, or more precisely, n+1 valued Lukasiewicz logic is pre-complete, as it's called, if and only if n is a prime number. And pre-complete just means it's not functionally complete, so you cannot express all the possible truth functions over the n+1 values. But if you add any function that cannot yet be defined, then it will be complete. So you see, I mean, it's just an example. You do have interesting questions of this kind, even for propositional logic. Still, you might complain there are no quantifiers, so it's still something quite different. Now let's add the propositional quantifiers. And again, what you will see, it's quite different from the classical case. In the classical case, we have quantified Boolean logic. And of course, there's no real increase in expressivity. You can easily eliminate the quantifiers, just replace by the disjunction, where you replace the variable in one disjunct by falsum, in the other by verum, and that's the same thing. Of course, you have much more succinct formulas for the same thing that you want to express. But in many value logic, usually you have much more. It's not just about succinctness. You really increase the expressibility of the logic. So I hope, even if this started out to look quite silly, you see that there are a certain number of topics that are related to what people are interested in finite ball theory, and actually sometimes it's even the comparison here goes even deeper, because the techniques to address these problems, complexity, games of different kinds, comparison games, semantic games, are partly related also methodologically to finite model theory of the usual kind. But even if you are not agreeing with me on that first topic, I'm sure that the second one, 0-1 laws, you will agree that certainly in the center of interest for finite model theory. And today we actually heard in the first two talks quite a lot about 0-1 laws for many value logics, right? And that's also, incidentally, also the place where I can clarify why I'm even here. Guillermo gave it away already a little bit, namely, it's a bit embarrassing because it's really, I think it must have been some 15 years ago. I know that the paper that Guillermo and Carles are referring to is not so old, but about 15 years ago, I was reading a great book, a very inspiring book, and you know it, Leonard Lipkin, Elements of Finite Ball Theory. And I asked myself, 0-1 laws, are they also possible for something like Vukovic logic. And I just observed that you can encode many value structures uh, uh, in using classical logic. So just by this coding trick, which is straightforward, I mean, it's a very easy exercise. You can transfer the classical 0-1 law into a limit law of the kind that you've seen today already, and I'm referring here to a version paper from Guillermo and Carles from last year, where you can paraphrase. Well, I'm not precise here, of course, but you've seen this, so you will understand any first order formula, possibly even infinite with finite variables. It's also applying to that kind of formulas, takes a certain truth value almost surely and avoids every other truth value almost surely. So this applies to a wide range of logics. In other words, my little observation, which is a bit silly because anyway it doesn't work for all the finite value logics that I was aiming at, is but more than just generalized. It's really put into in the context of a much more systematic and much more extensive kind of research. And anyway, so Robert Kosick was a project assistant at some time, and he wanted to join a conference in Thailand, I still remember. So he told me about this conference, and he had no topic, and then I just told him about my observation, and so he wrote it up, and that's why this paper came into existence. Okay, so what is really interesting here, at least to me, and I hope you will agree, is that it's not just, and I'm talking here, of course, about the result of Guillermo and Carles, and it's partly also referring, as I learned, basically today, it's including what we learned today in the nice talk by Casaido. So there are interesting differences to the classical case. It's not just about generalizing the classical scenario. There are related questions, of course. I mean, generalizing, that's obvious. Yeah, I don't even want to go much into that. But another question that I kind of independently asked myself already quite a while ago, so which truth values can emerge now as limits? So you have this 0-1 law, but which truth values can emerge? And we heard a lot about this actually in a very nice talk by Professor Caicedo today. There's a more speculative kind of relation, namely, you can also have truth values emerging as Nash equilibria in imperfect information games. And that's a similar story, but yeah, well, okay, I better move on. I'm looking a little bit on the watch. I should move on to the next topic. Model comparison and related games. I think you all agree that's also very much of interest. It's very much part of what we do in finite model theory. And again, there's nice work on back and forth conditions, not just for finite models, but for arbitrary models in many value logics. My reference here is this paper, and I think this is really the one to look at by De Lunde, Garcia, Zerdania, and Noguera. And to my knowledge, maybe Carles can correct me, but it was not done in terms of games. Yeah, it's just looking at the conditions independently of Ehrenfreich per se type games. So one could ask, what does a game version look like? And it's again, it's quite interesting because there's more than just one possible way to formulate the back and forth conditions. So which are the most appropriate for this kind of endeavor? Which types of many value logics can be covered? I think these are all interesting questions. More speculative, but maybe even more interesting, there's graded equivalence once you have weighted structures, and even satisfaction. Even if you start with semantic games, so simply evaluating in a game style, you will realize that a game will give you not just a win-lose, takes the designated value 1 or not. You can do that in child's game, but what is more interesting, it gives you the degree to which given formula is satisfied in a structure that's well defined. And I suggest that one can study here questions that are simply not don't have any room in the classical case. It might be interesting. And of course, you can also go on to second order logic, quantified propositional logic. Again, I think in many valid case, interesting open problems are lurking here. What I find most interesting, I mean, this is now a personal remark, is that in a standard fuzzy logic, even if you restrict to finite value logic, it's not just the existential and the universal quantifier that are of interest. What you really want to have is fuzzy quantifiers or semi-fuzzy quantifiers, meaning your scope formulas are still classical. And so you can even talk just about ordinary classical structures using a many-valued logic to express things like almost all, about half of the elements, etc. And I think it's not yet well studied what exactly is the expressibility of these groups of logics, and looking at fuzzy quantifiers, in particular semi-fuzzy quantifiers from the point of finite model theory, that's also what I want to suggest. So topic number 4, extension variance of first order many value logics. Of course, that's just looking at classical finite model theory. You do study there, not just, it's actually not so interesting to look at standard first order logics. You look at certain types of extensions, infinite formulas with finite variables, fixed point operators of different kinds, second order quantifiers, and others. And that triggers obvious further questions. So how to do that for many value logics? Is it interesting? So even just thinking about something like graded transitivity, I mean, a case where in principle we know how the operator should be defined. I started to look at it briefly, and it seems to me it's quite a challenge actually to get a really robust and interesting grip on these kind of extensions here. So of course the challenge is always not to just generalize for the sake of generalizing. You really want to understand better, for example, what gradedness can add to the expressive power. In what does it mean, for example, to have fuzzy quantifiers again, generalized quantifiers? Does this, in which sense does it add to the expressivity? Okay. Topic number 5, some would say, and I can very well understand, that this is the real aim of finite model theory, of classical finite model theory. We want to capture complexity classes, descriptive complexity, and we should start with this observation of Trachtenbrot that of course you cannot single out recursively or even recursively and enumerably the finite models. I don't know whether it's so well known that Hayek already in 98, I think Carl has mentioned it at least indirectly, he had a paper where he explicitly talks about Trachtenbrot theorems for fuzzy logics, for Vukosevic logics and other standard fuzzy logics. What about Fagin's theorem? Well, just an almost trivial observation. It does hold for standard many-valued logic, at least if you have delta, because then immediately you can do everything that you can do in the classical case anyway. So the hard part of proving it, namely hardness, is for free now, because you just take it over from the classical case, and then you can still evaluate your formulas polynomially, at least, well, we have finite value logics, of course. Okay, that's a trivial observation. But what about less trivial or much more open topics of research, like classifying not just the formula side of things, so to speak, but the computation side. So we have a logical side in this problem of capturing complexity classes, and we have a machine side, if you like, a computation side. And there's lots of literature on fuzzy Turing machines, weighted automata. That's particularly interesting, I think, fuzzy finite automata. So I have no time to go into any details, but I hope you see what I'm suggesting here, what could be studied. Now, my last group of topics actually is not really a group. It's 5 selected almost randomly, but at least I wanted to order them from already familiar or already on the table to highly speculative and maybe not, just an idea. So here's one of these familiar ones, familiar in the sense not of well known, it deserves to be much better known. This paper, again by Guillermo and Carles on Freyse classes of graded structures, but at least it has already been done. And I think Guillermo and Carles will agree. There's related questions to be asked. A similar story, the simmering semantics that we hear about today so much, in particular by Erich Rehl, fascinating work, I think. That's a topic that's certainly not yet closed, as we hear. And then also that was mentioned a bit. The random graph in the classical case, yeah, a central tool. What about the random weighted graph? Here, this is more speculative. So unreferencing games yield Lindstrom theorems. That's a recent paper by Cheng Liao. And I asked myself when I read this, can this be generalized to many value logics? Because it does apply in this formulation to what he calls Boolean logics. And I think interesting things could be done along this line. Now, finally, I'm already close to the end of the time that I wanted to spend here. Really, finally, what about relations between probabilistic models of computation and graded structure many-valued logics? A lot could be said about that. I think we are just starting to see some interesting relations here. Okay, so this is my last slide. Summing up, I will not use the time to just read that to you. Of course, you can take different perspectives on the topic. I just gave you one, but I hope you can all agree it's early days for finding model theory of many value logics, and that's how I want to conclude.